This is a simple video on considering the problem on discrete time convolution. Let us go on to the problem. Find the discrete convolution of two inputs. The first input is x of n, that is going to be equal to u of n minus u of n minus 4. By now we are quite familiar with what could be the value of u of n minus u of n minus 4. The value is going to be 1, 1, 1, 1. The second input is h of n is going to be equal to delta n minus delta n minus 2. So here the input is going to be equal to 1, 0, minus 1. As delta n is 1 and delta n minus 2 is minus 1 and delta n minus 1 is 0. So the convolution states y of n is going to be equal to x of n convolution h of n. This is given by the formula y of n is going to be equal to k equal to minus infinity to plus infinity x of k into h of n minus k. We have already seen that k is a dummy variable and n minus k is the shift that is introduced. So let us go on to see how this could be implemented. So let us try to apply this to the first value, that is when n is going to be equal to 0, y of 0 is going to be equal to h of k, x of k into h of 0 minus k, which means it is x of k into h of minus k. H of minus k is the reflected or time reversed version of the impulse input. So let us go on to just represent what could be x of k. The problem states that, just for the refreshing, it is given by x of n is going to be equal to 1, 1, 1, 1 and h of n is going to be equal to 1, 0, minus 1. So let us try to represent x of k and h of minus k and then do the convolution. Only 3 steps are involved in each stage. So x of k is going to be equal to, at n equal to 0 it is 1, at n equal to 1 it is 1, at n equal to 2 it is 1 and at n equal to 3 also it is 1, as can be seen here. Next let us try to represent what could be h of minus k. When we have h of minus k, this could be represented as could be seen here. At 0, 1 and 2, h of k would be 1, 0 and minus 1. When we try to reverse it, this would be 1, 0 and minus 1. Now let us try to evaluate y of 0, which is going to be equal to, y of 0 is going to be equal to x of k into h of minus k. What happens to such a problem? Then we are just writing each of the values at their respective positions, which means at n equal to 0 it is 1, at n equal to 1 it is 1, at n equal to 2 it is 2 and at n equal to 3 it is 1. Similarly here it is 1, here it is 0 and here it is minus 1. So when we consider the multiplication we get the result only at this point, hence the answer is 1. So y of 0 is equal to 1. This is our first discrete convolution answer. Next, let us go on to see what would be the discrete convolution at n equal to 1. At n equal to 1, the expression becomes y of 1 is equal to x of k into h of 1 minus k. So let us now try to do the same steps. That means represent x of k, represent h of 1 minus k and then find out the convolution. So for representing x of k, the steps given is as in the previous case. It is at 0, 1, 2 and 3 the values are 1, 1, 1 and 1. Let us try to now represent h of 1 minus k. From our previous case we have got that h of minus k is going to be equal to at n equal to 0 it is 1, at n equal to minus 1 it is 0, and at n equal to minus 2 it is minus 1. So h of minus k minus 1, or as can be seen, h of 1 minus k means since it is a positive shift, this 1 tells that we have to shift in the right direction. Or if we are going to consider it as h of minus of k minus 1, we are just shifting it towards the right. So in both the cases, whether it is h of 1 minus k or h of minus of k minus 1, both means that the signal which is there in the previous stage has to be shifted towards the right. That means positive time axis by 1. So we get it as minus 1, 0 and 1, which means there is a shift from 0, it gets shifted to 1. From the time index of minus 1, it gets shifted to 0, and from the time index of minus 2, it gets shifted to minus 1. Now let us try to evaluate the convolution solution for the value of n equal to 1, which is going to be given as y of 1 is going to be equal to x of k in convolution h of 1 minus k. Hence, the answer would be at n equal to 0 it is 1, at n equal to 1 it is 1, at n equal to 2 it is 2, and at n equal to 3 it is again 1. Similarly, h of minus of k minus 1 is going to be equal to at n equal to 0 it is 0, at n equal to 1 it is 1, and at n equal to minus 1 it is minus 1. We have rewritten it in the same case. So when we multiply, the only solution we get is at n equal to 1, which means our all other terms turn out to be 0. Hence the value of y of 1 is going to be equal to 1. Let us now try to go on to the next step, that is, let us try to evaluate the next value of the discrete convolution, which means at n equal to 2. Hence we need to get the expression as y of 2 is going to be equal to x of k convolution h of 2 minus k. By now we are familiar with what we need to do. X of k remains the same. It remains as 1, 1, 1, 1. The only thing that is going to get shifted is the second term. After shifting the second term, we need to multiply and add if necessary. If other terms are 0, the addition term is ignored. So let us try to go back and represent x of k as it is the normal practice. So at n equal to 0 it is 1, at n equal to 1 it is 1, at n equal to 2 it is 1, and at n equal to 3 also it is turning out to be 1. Next, let us try to represent h of 2 minus k. When we want to represent h of 2 minus k, we need to start from our previous step, which is h of 1 minus k or h of minus of k minus 1. Let us see what happens in the previous case. It was obtained as at minus 1 it was 1, at 0 it was 0, and at 1 it was 1. So now, since we need to shift by, the previous one was h of 1 minus k, now we need to shift by one more towards the right as is seen in both the cases. Hence we have shifted it to the right by one position, which means the value which was at minus 1 now becomes at 0. 0 which was at 0 now turns to go to the index of n equal to 1, and the value of 1 which was at index n equal to 1 now goes to the index of 2. This is what happens during the second stage, which is the most crucial stage, obtaining the value of h of 2 minus k. Next, let us try to evaluate as is in the normal case. Y of 2 is going to be equal to x of k convolution h of 2 minus k. Hence, this turns out to be, obtaining from the same values, we have got it as 1, 1, 1, 1 for 0, 1, 2 and 3, and here it is minus 1 at 0, at 1 it is 0, and at 2 it is 1. So when we multiply, we get this as minus 1, 0 and 1. Till now the summation was not there because other values used to be either 0. So this turns out to be minus 1 plus 0 plus 1. So the last stage is the summation of the result got in this stage. Hence the answer for y of 2 is going to be equal to 0. Let us now try to evaluate the next term, which means at n equal to 3, what would be the value of y of 3? From the expression, we know that y of 3 is going to be equal to x of k into h of 3 minus k. By now we are quite familiar with what are the steps. Represent x of k, represent h of 3 minus k, and then obtain the convolution. Let us go on to the various steps. Represent x of k, which means it is 1, 1, 1, 1 at 0, 1, 2 and 3, and h of 3 minus k is obtained from the previous stage, as can be seen in the previous case. That is, earlier it was at 0 it was minus 1, at 1 it was 0, and at 2 it was again 1, which was h of 2 minus k, or as can be seen here, h of minus of k minus 2. So h of 3 minus k is going to be just shift all these values by one position towards the right, which is what we do. Hence at 0 it gets shifted to 1, and the value at n equal to 1, which is 0, now gets shifted to n equal to 2. So it is obtained here, and the value which is there at n equal to 2 now gets shifted to 3. Hence the values are, as is obtained, it will be obtained only at 1, 2 and 3, which means this is what we need to do in the next stage. We need to multiply this 1 and minus 1, this 1 and 0, and again this 1 and 1. There is no term at 0, hence the value of 0 is going to turn out to be 0. Let us see how this is going to be done. So obtaining the value of y of 3, it is going to be equal to x of k into h of 3 minus k. Let us go on to see what could be the values. It would be obtained as was mentioned earlier, 1, 1, 1, 1 at n equal to 0, 1, 2 and 3, and here the value starts at 1. So at the indice of 1 it is minus 1, at the indice of 2 it is 0, as can be seen here, and at the indice of 3 it is 1. So when we multiply, 1 into minus 1 is minus 1, 1 into 0 is 0, 1 into 1 is 1. So the value of y of 3 again turns out to be 0. Sum of all these elements. Let us now try to evaluate the value of y of 4, which means at n equal to 4, y of 4 is going to be given by x of k into h of 4 minus k. By now we are familiar with the procedure, which means represent x of k, obtain h of 4 minus k from h of 3 minus k, and then perform the convolution. So what happens? Represent x of k as is in the normal case at 0, 1, 2 and 3. The values are 1, 1, 1, 1 respectively. At h of 4 minus k, this is what is going to be our next step. Let us try to obtain h of 4 minus k. This is got as h of 3 minus k is taken from the previous case, and we are shifting to the right as is seen in the previous cases. So let us see how this is going to be done. H of 3 minus k, or h of minus of k minus 3, was obtained as minus 1, 0 and 1 at n equal to 1, at n equal to 2 and n equal to 3. So h of 4 minus k, or h of minus of k minus 4, is equivalent to shifting right by one position, which means the value which was at n equal to 1, that is minus 1, is now becoming shifted to 2 as minus 1, and the value which was at n equal to 2, which was 0, now gets shifted to n equal to 3, and the value which was at n equal to 3 now gets shifted to n equal to 4. That means we have got h of 4 minus k from h of minus of k minus 3, or from h of 3 minus k. Let us perform the next step, which is x of k into, or convolution, h of 4 minus k, which is the value of y of 4. This is got as at n equal to 0, the value of x of k is 1. At n equal to 1 it is 1. At n equal to 2 it is 1. At n equal to 3 also it is 1. And h of minus of k minus 4 or h of 4 minus k is obtained only at n equal to 2, which means at 0 and 1 we did not have any values, as can be seen here. So at n equal to 2 it is minus 1, at n equal to 3 it is 0, and at n equal to 3 it is 1. So let us try to multiply each of the terms. 1 into minus 1 is minus 1, 1 into 0 is 0. Here we have no term, so this is also ignored. Hence the value of y of 4 is going to be minus 1 plus 0, which means the value of y of 4 is going to be minus 1. Let us now try to obtain what is going to be the value of y of 5, which means at n equal to 5, the expression is given as x of k into h of 5 minus k. Represent x of k, represent h of 5 minus k, and perform the convolution. Representing x of k, we get it as 1, 1, 1, 1 at 0, 1, 2 and 3. The major step is representing h of 5 minus k, which is as usual done by taking the values from the previous case, which means from h of 4 minus k or h of minus of k minus 4, which was obtained in the previous case at 2, 3 and 4, at minus 1, 0 and 1. So now it is going to be shifted by one position to the right, which means h of 5 minus k is going to be obtained from h of 4 minus k by shifting everything right one bit or one position, which means from minus 1 it goes at n equal to 2, it goes to n equal to 3, and the value of 0 now gets shifted to 4, which was earlier at 3, and the value of 1, which was at n equal to 4, now gets shifted to n equal to 5. Now let us try to evaluate y of 5, which is going to be equal to x of k into h of 5 minus k or h of minus of k minus 5. The values obtained are going to be equal to, at n equal to 0 it is 1, at n equal to 1 it is 1, at n equal to 2 it is 1, and at n equal to 3 again it is 1. Here mind it, h of 5 minus k starts only from minus 3 at n equal to 3. So the value starts at n equal to 3. So it is minus 1, 0 and 1. So the value is going to be 1 into minus 1, which is going to be minus 1. The value of y of 5 is going to be equal to minus 1, which is the value which is obtained on multiplication. Any guesses what would be the value at n equal to 6? At n equal to 6, again it is going to be shifted by one position, which means the value of h of 6 minus k would start from 4. Let us see in detail. At n equal to 6, as has been mentioned, y of 6 is going to be equal to x of k into h of 6 minus k. X of k remains in the normal case, and let us try to now focus on what would be the value of h of 6 minus k. From the previous case, we have that h of 5 minus k or h of minus of k minus 5 is starting at n equal to 3 and it ends till n equal to 5, given by minus 1, 0 and 1. Now it would get shifted by one position to the right, which means from minus 1 it goes to, at n equal to 3 it goes to 4, from 4 it goes to 5, similarly from 5 it goes to 6. Hence this is going to be what is going to be the output. When we multiply, the positions of x of k remain from 0 to 3 and the values of h of 6 minus k starts from 4. So what would be the multiplication solution? Without going to the solution, we can say that the answer is going to be 0. Let us see how this is obtained. At n equal to 0, 1, 2 and 3, it is 1, 1, 1 and 1, and at n equal to 4, it starts at minus 1, at n equal to 5 it is 0, and at n equal to 6 it is going to be 1. So there are no common elements where we can multiply, hence this is called as an overlap concept, which is going to be considered as an important thing, and we can see that any shift hereafter is going to result in a value like this, which means y of 6 is 0, and the same is applicable for y of 7, y of 8 and so on, which means for any value greater than or equal to 6, the value of y of n is going to be equal to 0. Now let us try to evaluate the discrete convolution for n equal to minus 1. So y of minus 1 is going to be equal to x of k convolution h of minus 1 minus k, which means it is x of k convolution h of minus 1 minus k, representing x of k as in the normal case at n equal to 0, 1, 2 and 3 it is 1, 1, 1, 1. The most important part is representing h of minus of k plus 1, and we would recall that h of k is given by minus 1, 0 and 1, and h of minus k is given by minus 1, 0 and 1, which means we are deviating slightly from the usual procedure. We are going back to the start because it is going to be the negative half of the time axis or the right side of the time axis, and hence we start from h of k, obtain h of minus k, which is got as minus 1, 0 and 1, and then shift as is seen here. It could be again shifted left by one position, which means the values at n equal to 0 is getting shifted to minus 1, the value at minus 1 is getting shifted to minus 2, and the value at minus 2 is getting shifted to minus 3. Thus we are getting the values at minus 1, n equal to minus 1, at n equal to minus 2 and minus 3 as 1, 0 and minus 1. Now let us try to evaluate y of minus 1, which is going to be x of k into h of minus k plus 1. Recall that the values of x of k start from 0 and the values of h of minus 1 minus k start from minus 1. As can be seen in the case of n equal to 6, there is no common factor where there could be a multiplication. Hence, without doing it, we could say that the result is going to be 0, which means y of minus 1 is going to be 0. This is what we have obtained. Hence, we are getting it as n equal to 0, 1, 2 and 3. It is 1, 1, 1, 1, and here it starts from minus 1, minus 2 and minus 3. There is no overlap as can be seen in the previous case. Hence, the result of y of minus 1 is going to be equal to 0. This is the same case that we will get if we proceed as y of minus 2, y of minus 3, so on, and in each of the cases we would get the values as 0 only. So now let us go on to make a conclusion of the solution. The solution states that, can we say that y of n is going to be equal to 0 when n is going to be less than 0. The next value obtained is for values between 0 and 5, which was seen in the previous case. We have just consolidated it. It is 1, 1, 0, 0, minus 1 and minus 1. And for n greater than or equal to 6, we have obtained that y of n is going to be equal to 0, and thus the results of the convolution can be quickly summarized as at n less than 0, y of n is 0, at n greater than or equal to 6, y of n is 0. The values of the convolution exist only between 0 and 5. Thus, going for our references, Oppenheim and Simon Hinckley.